Alright, hi everybody. My name is Janie Clayton. I have my giant, little list of credential things here. I recently started working for Black Pixel. Black Pixel is a consulting company that does a lot of really prestigious iPhone apps that I can't talk about because it would violate our NDA. I am the co-author of a couple of iOS books, and I also am the co-host of NSBrief. If you want to get a hold of me, my Twitter handle is RedQueenCoder, and I blog at redqueencoder.com. So a little bit over a year ago, I started working for a company called Sonoplot. Sonoplot was founded by a developer named Brad Larson. Hopefully you've heard of him before. I told most of you about him, but he had one of the first 500 apps out in the App Store. He created a molecular modeling application that he created in 3 weeks with OpenGL. He is a moderator on Stack Overflow, and he is the creator of GPU Image. So he's a really good programmer, and he knows a lot of different things about technology. So back in 2004, he founded this company that does robotic systems to do microscopic fluid printing. This is based on technology that he discovered while he was getting his PhD in materials science. Our robotic systems utilize ultrasonic frequencies to accurately dispense tiny, minute amounts of fluid. Our robotic system has a resolution of 2.5 microns. That's like super, super tiny. And so this has been our system that we've had for the last, I think, about 7 or 8 years. Originally, the software was written in C++. But back in 2007, Brad had heard a lot of people talking about Next and heard people talking about Objective-C in the scientific community. And he was kind of interested in the technology to see if it would be a better way for him to go and write all of his software for this system. So back in 2007, he threw out all of the code that we had before, and he rewrote all of our code in Objective-C. And this was a really good decision for the company. It was a lot more maintainable than C++. It was a lot easier to maintain one platform instead of trying to make it work on a lot of different platforms, and this worked out really well for him. But he kind of noticed over the years that as the code base got larger and larger, it got a little bit more unwieldy. There got to be more and more subtle bugs. There were certain parts of the code that were kind of fragile that couldn't actually be changed or upgraded. So I mentioned that Brad created GPU Image. He wanted to put GPU Image in software for the microplotter, but he wasn't able to do that because the camera code was so fragile that it could not be changed. And just things like they started having worse and worse bugs that were happening more and more often. Then 2 years ago, he took over as CEO of the company, and he just didn't have time to go in and patch and fix all of these bugs that were in the Objective-C code. So last year, they brought me on to come in and kind of go in and patch the bugs and kind of maintain the software because he just didn't have time to do it any longer. So when I started last year, I kept hearing him talk about how much easier everything would be if we just did it in Swift. And I was there for about 2 months, and I wanted to try to implement the Reactive Cocoa framework because it sounded a lot like what he wanted to do with the code. He kept going, Reactive Cocoa sounds really cool, but I'd really rather do this in Swift. And so I'm like, okay, I've been here for 2 months, and we're not implementing anything to go and fix some of these things. And I just kept hearing it. It would be really great if we could just do this in Swift. So finally I was just like, dude, just freaking do it in Swift then. So then after doing a little bit of an assessment, he went in and determined that we were going to then spend the next 10 months converting our software to Swift. We're going to throw out the Objective-C software and we're going to rewrite it in Swift. He wrote up a blog post that it got retweeted by this one guy that people may or may not have heard of, whatever. And so he did an assessment and figured out that 40% of the bugs that we'd had over the last 3 years wouldn't even have been possible if we just written the software in Swift. So we didn't have unit tests available. One of the things I was hired to do was to write unit tests, but just all of our code was mixed up together. We had spaghetti code, we had the fat horses. There was not a lot. There was just no way of writing unit tests and being able to go in and fix things. And we have bugs that we don't even know how they got to be. So I know that Kirby can't read this because he's having the problem with his glasses. This is NS alert with error called with a nil NS error. A generic error message will be displayed, but your user deserves better. We still do not to this day know what is triggering this error because it is so like buried in all of our code that we can't go in and fix it. And you know what? The user does deserve better. So some of our common issues that we had that I'm going to be talking about today and how we were able to resolve them were we had silent nil messaging failures. This was something that was seen as an advantage in Objective-C over C++ that we kind of determined over the last couple of years didn't necessarily work out for us. Faith-based casting. So we didn't have any type safety. We weren't certain if we were going to be getting the type of data we needed to be getting, and that was not something that could be assured with Objective-C. Unexpected object coupling, which again is the nice spaghetti code, not being able to test each and every part of the app all on its own. And then error handling problems. I know Melissa briefly talked about error handling yesterday, and I'm going to spend a lot of time telling you about how we implemented error handling in our application. That was actually one of the first things that Brad was interested in looking at when he was going and dealing with Swift, was how to deal with errors. So I'm going to be going over how we implemented all of these in our code and how it made our code a lot better. Nil, the silent killer, also known as the $10,000 bug. We had a bug that was caused by nil messaging errors that caused $10,000 worth of damage to our systems. So it's silent failure, feature, or bug. Like I was saying before with C++, a lot of people really got angry with C++ because if you had a nil dereferencing error, it would completely crash the application. It was a real pain in the ass to go through and actually check everything to make sure that your app wasn't going to fail if you had a nil messaging error. So when you had Objective-C, instead of having the application crash if you have a nil value that you expect to have something actually in it, it just kind of sends it off to nowhere. So Objective-C was based on message sending. So basically, if you had this message and you sent it off to an object that didn't exist, it just kind of went off into nowhere, and everybody kind of figured that it wasn't a big deal because it wasn't affecting anything because it just got sent to nowhere. So you wound up with something like this, where you have all these nil messages that are out in the middle of the jungle, and nobody knows nobody ever got them. So normally we were thinking that this was a good thing, but it's not necessarily a good thing if you need to make sure that you have a piece of hardware that is receiving a message about where it is supposed to be. One of the problems that we have is if you receive nil and you are in Objective-C, there are default values. So if it's a descendant of NS object, it's just nil. However, if you are a number, it sets a default value that is usually 0. If you think about an XY axis coordinate system, and you have 0 and zeros down here, and you have a dispenser, and the dispenser has to come down, and it comes down to 0, bad things happen. Harry Potter must not go back to Hogwarts. So basically, we had nil messaging errors that were being sent to the z-axis that were then taking this nice expensive dispenser head, this nice expensive camera, and they were jamming them down into the deck of our systems. So we were going and having $500 cameras being smashed left and right because we had a nil messaging error in our software that was sending a signal to the z-axis to go to 0. And 0's down here. We want it up there. That's an example of why having required values is a good thing. I know that when we first started with Swift, everybody was kind of like, oh, this is kind of stupid. We don't like the fact that we have to go in and verify this stuff because we just hadn't done it before. But if you're dealing with a piece of hardware, you want to make sure that the hardware is actually going to where it needs to be. You have compiler-enforced rules that ensure that your values are compliant, or else it won't even let you build. So that error that we had before that caused $10,000 of damage isn't even possible with Swift because it just couldn't happen because we can write the code in a way that we tell it this is not an optional value. So my analogy about this is it's a little bit like organ donation. So in the United States, we have it where you have to opt in for organ donation, and we have an organ shortage. But then in other countries, you have to opt out, and they don't have an organ shortage. In Objective-C, you had to opt in to having a constant value. The default was that your value was never a required thing. But in Swift, you have to opt in to making it an optional value. And this makes things a lot safer. It makes you actually think about your code and think about what it is that you're doing. So instead of just having to be like, oh, it might be optional, you have to actively decide, there is a reason that this needs to be optional, and you have to actually go in and do something special to it to make sure that it is optional. So now that we are able to make sure that all of our values that we absolutely need to not be optional are not optional, we don't have the issue of the $10,000 bug anymore. And anything that you can catch in the compiler, as opposed to unit tests, as opposed to being out in the field, it's a lot less expensive to fix it before it gets out and causes a lot of damage. I mentioned a little bit about type safety in Swift. So it prevents faith-based casting. So you know what you're getting because the compiler goes and enforces to make sure that you're getting the right types. So like in Objective-C, you can have NSArray, and NSArray can be filled with anything. You don't necessarily know what it's going to be filled with, and you might be getting a type of value from it that you don't necessarily want and won't work for what you're doing. You make sure that all of your pieces fit together because each thing can only take a specific type and only return a specific type, and so you're ensuring that the chain of functions are all receiving and returning what it is exactly that you want it to have. So I know you'd asked a little bit about serialization in Swift. I'm going to be showing an example of how we did property list serialization and we replaced NSCoder with Swift. So I don't know if this will be helpful to you or not, but hopefully it will. So we have a bunch of coordinates that we want our users to be able to save, like for where they have their solution well and where they want to go and they want to print their materials on the substrate. We want them to be able to save this, and we didn't want to have to go in and implement core data because core data was a little bit too heavy duty for what we wanted to do. So we send things to the NS user defaults in the property list so that we can go and we can read through it. If you ever read through any of the iOS books that are out there and they talk to you about serializing data, they always tell you to use NSCoder to convert types to NS data to be stored and extracted later. NSCoding has a couple of problems with it. So it doesn't have any type safety. One of the big things that they talk about in all of the security talks at WWDC is talking about this problem with NSCoding and your user data. You can have somebody put an executable file in something like the NS user defaults, and it will be uploaded to somebody's computer, and it can cause a buffer overflow, and bad things happen. And there's no way in Objective-C to be able to go through and make sure that you're only getting the data that you want and to make sure that nothing malicious or corrupted comes into your application. NSCoding also only works on descendants of NS objects. As Melissa was talking about yesterday, the Apple people are kind of like encouraging us to get away from making everything into a class. They want us to start using structs and enums. And since structs and enums are not descendants of NS object, you can't directly store a struct into NS user defaults by serializing it using NSCoder. And then NS data is essentially like this gray goo. So it's this giant like blob of bits and bytes that you can't go into and actually look at it specifically to make sure that it's the exact types of bits and bytes that you want. So serialization is a little bit like the transporter from Star Trek. It takes all of your little molecules and it packages them up in a nice little package, and then it sends it off somewhere else, and it goes and it puts it back together again in the right order. So I'm going to talk to you about how we went and did that using Swift without using NSCoder. So first off, we made our coordinate a struct. Since we wanted it to be a value type instead of a reference type, it was important that we made sure that this was a struct. We also didn't need all of the overhead of creating an object. So our coordinate has just three properties. There's an x, a y, and a z. And those are all doubles. And then we have an initializer for the x, the y, and the z. So this is our starting off building block of our coordinate system that we're putting together to save to the NS user defaults. We also created a protocol for property list readable because coordinates aren't the only things that we want to be able to save to our NS user defaults. We want to be able to save a couple of other things, and all of them need to go through the same process. So the process that we needed to make sure that everything conformed to is we needed to make sure that it had a failable initializer and a function that had a property list representation. So over here is how we implemented our extension for the property list readable. And I know you're probably noticing these little green boxes. These boxes are showing different things that we were able to add to the code over the last year or so that were introduced in different versions of Swift. So we have the failable initializer that was introduced in 1.1. We have the nice if-let syntax that was released in 1.2. And then we have our nice spiffy guard statement that we heard about yesterday that was released in 2.0. So the top function, the property list representation, is what we use to serialize our data to be sent to the NS user defaults. it takes our coordinate object, it turns it into a dictionary where we have a key, which is the x, the y, which is the whichever axis that we're on, and then whatever the value is for that. And then it returns a nice NS dictionary. So now we have a nice object that's descended from NS object that can now be stored into the NS user default. So we were able to get around the whole not being able to store a struct directly to the user defaults by turning it into an object. Magic. So then down here, you have to deal with deserialization. So you have to deal with if you pulled something out of the NS user default, and you want to make sure that it complies with your coordinate object. So we take our coordinate and we run it through this failable initializer. We're making sure that we actually have something that got passed into the function. If we don't have anything that got passed into the function, there's no point in continuing with this, and we just return nil. Then we go through and we check to make sure that every single one of these values is present within the object that we sent into the coordinates. If any of these is nil, this immediately kicks out and returns nil for the entire thing, and the entire coordinate fails. Only after checking to make sure that we have an x, a y, and a z do we return and set the x and y, z coordinates for this coordinate object. So we were able to pull it out and make sure that before we create a coordinate struct, that we actually made sure that all of the things were present that we needed in order to create the coordinate. So this prevents malicious code from being brought into our application from the NS user defaults. Now, in order to save our code to the NS user defaults, we go through and we use the nice fancy map function. So we're going through, we're taking every single item that we have in our array, and we are applying this properties representation function to it. So it's going through, it's taking all of our coordinates, it's converting them into nice little happy NS dictionaries, and then it's returning them and setting them to the NS user default. So we're saving them out, making sure that they're objects and that everything is compliant. So if everything went right and we went and we saved this properly to the NS user defaults, we're going to have something that looks kind of like this. So we'll have a key of saved positions that then has an array of a bunch of NS dictionaries that are all representations of coordinate objects. So we're hoping that after we save that out to the defaults, that that's what we're going to get back. So then we have to go through and after we extract the values, we have to go and we have to filter through them to make sure that every single one of them is an actual coordinate object and not a malicious piece of code. So we go in here, and again, we have our nice little guard statement where we're going through, and we're making sure that our property list array can be cast as an NS dictionary, and if it's not, then we'll return an empty dictionary. So if we get back an array of something else that cannot be cast as an NS dictionary, the entire thing will fail and return nil. Then we go through, after we verify that we actually have an array of NS dictionary objects, and we map them to this property list representation. We filter out anything that fails, or anything that's nil, and then we remap it and we unwrap it. Now, this is a pretty kind of slick piece of code, but you know what? It's a little clunky, and I think that maybe it could be a little bit better. So specifically, we look at this. So we have this array, we're going through, we're running it through a function, we're checking to see if anything's nil, and then we're unwrapping it. This is a common thing that you think that people would be doing over and over again. You'd think there'd be a better way of writing it instead of having to chain these three functions together. Well, hey, guess what? There is. Flat map. So instead of having to go and call the map, the filter, and the map in order to go and unwrap all of the now non-optional values, we can just run flat map, and flat map does everything that those three functions did, and you get it in one line of code instead of like that many lines of code. That's pretty slick. That's not the only thing that we could do to improve that particular function. So we have this guard, let, encoded array. We're basically going and we're checking to make sure that every single thing in this array is an NS dictionary. And if one thing is not an NS dictionary, then we throw the whole thing out. But that kind of stinks, because if you have 100 things in an array, 99 of them are dictionaries and one of them is a malicious piece of code, you're basically telling the project that you're going to throw out those other 99 coordinates just because you have one piece of corrupted data. So we think that we can do this a little bit better. Instead of going and throwing it out if even one of the objects is not an NS dictionary, we're just going through and we're just making sure that we actually have an array. If we don't have an array, then we go and we return an empty array. So we're just going and making sure that we actually have data. And then after we go and we make sure that we have data, we then go through and then we filter it through the map again just to make sure that things are in this dictionary. This is a little bit different from what we were doing before, because before it was all or nothing. Either everything was an NS dictionary and we threw it out, but here, if we have one thing that is not an NS dictionary, it's simply a null. And we get to keep all of the other things that are proper NS dictionaries of coordinates, and we, again, go through our flat map function, and we're able to get out all of the actual real coordinates. So we were able to save a couple of lines of code and not throw out all of the valid data that we had just because one piece might be corrupted. That was pretty cool. And like I said, we did this to replace NSCoding. This is completely type safe. We are verifying that anything that we get back out of the NS user defaults is going to be what we want. We can filter out anything that isn't what we want, and we're able to verify that we're not going to get any corrupt code or malicious code coming into our application. And this was something that wasn't really possible with Objective-C. So that was a huge win for us. So I want to talk a little about reducing mutability. I know, back when I was learning how to code, I thought, variables, they vary. You're supposed to be able to change them. So whenever, oh, now we have variables that don't change, it's like, well, this is crap. This sounds really stupid. This, defeats the entire purpose that I thought we had of having a variable, was that it could equal a lot of different kinds of things. But mutability isn't necessarily always the best thing. I know, so Swift is a hybrid functional and imperative language. So it has features of non-functional programming, like being able to maintain state and have some mutability, because something like Haskell couldn't really work very well for our application because we have the robot, and the robot has state. The robot has certain states that it is in, and that is not something we'd be able to do with Haskell. But it's still a really good thing to be able to reduce mutability in our application. So one of my examples that I have is this nice little story about these little girls. So you have Sally. Sally has a basket and Anne has a box. Sally has a little apple, and she's going to go put it in her basket, and then she's going to walk away. Then Anne's going to be a little asshole, and she's going to go and steal her apple and put it in her box. So Sally comes back, and she wants her apple, but she doesn't know where it is because it got changed out from underneath her by this other piece of code. So this was a big reason that we weren't able to go in and unit test our application when we had it in Objective-C. It was because we had a bunch of stuff, we had a bunch of things that were all acting on the same mutable piece of information. So we had issues where the robot would think that one thing was happening, but then it would get changed by another piece of code, and then it would get changed out from under it, and we had possibilities of divide by zero errors on nil messages, and things that could cause a lot of damage to our robotics. So right now, we have it where nothing can read and write to the same object. We have we did have a little bit of state because we had to keep the robot, but we basically cut out mutability from our application in order to prevent a coordinate from being changed out from underneath it while the robot was in the middle of doing its processes. So we told the singleton fairy to go away because we do not want our code to be untestable garbage. I talked briefly about how we had untestable code. I was brought in to write unit tests for the Objective-C code, and there was a lot of it that I just couldn't write tests for because everything was dependent on everything else. We had just these big complex bits of spaghetti code, and it just wasn't possible to verify that we were sending out code that didn't have bugs in it because we couldn't test it. And now we have we recently finished this project. We have it feature complete as of I think 3 weeks ago. We have unit tests for most of our code, and we have the new code coverage tool in Xcode 7 that was able to go through and check all of our code to make sure that when we ran the unit tests that we were testing every single line of code that we had in our application. We had a couple of lines of code that we realized could never be called no matter what we did, and we realized they were superfluous, and we were able to get rid of those. But we feel a lot more confident about putting our code out in the field because we have fully unit tested it, we've tested every single part of it, and we know that it works. So I want to talk briefly about value types versus reference types. This is mostly for the people that are sad and still have to work with Objective-C and haven't gotten to play with Swift as much as they'd like. So basically in Objective-C, the only way that you could encapsulate data was to have it in objects. And I know I talk to a lot of people who are just starting with Swift and they kind of are writing Swift like Objective-C. They think that everything has to start out as a class, and they don't really kind of understand about why they would use a struct because they're thinking about structs the way they were in C. In C, structs were basically the closest thing you could get to objects, and you could only there wasn't really a lot that they could do. Enums weren't particularly powerful either. we're at a point right now where the difference between a struct and an enum and a class, it's fairly like amorphous. There's a lot of they have a lot of the same capabilities, and one of the big reasons that you should start thinking about switching to structs is because that seems to be the way that Apple's kind of wanting everybody to go. So Swift structs, like, they allow other ways of encapsulating data besides classes. So instead of having it, if you need to do inheritance, you don't necessarily need to use a class anymore. You can use a protocol. There are a lot of different ways of doing stuff. And right now, basically, the biggest difference between a class and a struct is that a class is passed by reference and a struct is passed by value. So in our code, we have a robot class because we only have one robot. We want to make sure that the same robot is being used throughout the entire application, instead of having a lot of different instances of the robot because we only have one robot. So that's one of the places in our code that we have a class. We've almost exclusively replaced everything else with structs because everything else needs to be like an instance of something rather than the exact same one that's being passed by reference. So when do you use a class? Use a class if you want to have shared references. Use a class if you need traditional inheritance. You use an enum if you want to represent distinct options, but then in all other cases, use a struct. So when in doubt, start with a struct, and if you figure out that a struct isn't going to work for you, then kind of go to something else. But I just kind of want everybody to kind of break the idea that they have to make everything into a class, because it's not the way we're doing things anymore. Apple's kind of trying to get us out of the habit of doing that. Embrace the struct. And error handling. Error handling was a pretty big thing that was introduced in Swift 2.0, and Melissa talked about it a little bit yesterday, and I'm going to elaborate on what she was saying a little bit. So back when we first started with Swift, like I said, one of the big things that Brad got really excited about with Swift was the idea of doing different kinds of error handling. The first code that he wrote for our new application was his own hand-rolled error handling code. So before we had error handling Swift 2.0, we actually rolled our own errors. Now I didn't think about error handling that much when I was learning code because nobody ever really talked about it. I noticed when I was doing tutorials that I'd see stuff like this, where they're telling you about how to do all this stuff, and then you get down here, it's like, handle bad response. Always handle errors. Sideways smiley face. And it's like, I don't even know how to do this. I was trying to find tutorials about how to handle errors, and everybody's like, oh, error handling is really important. But how do you do it? It's just really important. I understand that it's important, but how do you do it? I couldn't find any resources anywhere. I think when I was researching this talk, I was looking for error handling in Objective-C, and there was just nothing out there. Everybody talks about how important it is to handle errors, but nobody talks about when you're supposed to do it or how it's done, and it's like, okay. So first off, when is it important to handle errors? So you want to handle errors if you have an iOS application and you're interacting with the file system, you're interacting with the hardware, you're communicating over a network. So let's say you're creating an application that uses GPU image. GPU image allows you to filter photos you've already taken, and it also allows you to filter live video from a camera. So those are two instances specifically where you would want to have error handling, because the camera, even though it's on your iPhone, it's separate from your application. It's something that your application doesn't control because it's outside of the little application sandbox. And it's the same with the file system for your photos. Anytime you are reaching outside of your application to do something, even if it's on your iPhone, you need to make sure that you do error handling, because you don't have complete control over, you have complete control over your application and your code, but you don't have any control about what happens outside of your nice little sandbox. It's possible that things can happen that you don't have any control over, and you need to make sure that your code fails gracefully if it's put in a situation where it encounters something that it doesn't expect. Again, we had some problems with Objective-C error handling. The method and function can only return one value. So back in Objective-C, because we had this constraint where Objective-C can only return one kind of thing, we had to pass in a mutable pointer to an NS error. So once it was inside the function, it would go in and it would write something to that pointer, and then you would have to go and you'd have to read stuff outside of your function. So this was really not cool. This was not designed very well because it was dependent on things that were outside of your function. You had to go and you had to mutate stuff that was going on outside of your function, and that was not a really efficient way of doing things. I think it was the best that they could do with the constraints of the language, but it's kind of sucky that you had to do that. With Swift, you have tuples, and you have a way of returning more than one value. you're able to get around that constraint that existed in Objective-C. Magic constants. So we deal a lot with hardware. I was just working on unit tests for one of our motors. One of our motors has an error that is associated with the number 64. So if you send out a command and you get back a response of 64, that's an error. The only way that you know that is if you read the documentation, and it has like it's an amorphous thing that you don't necessarily know or have intuitive. You have to have like a lookup table of all of the things that might be errors. If you receive something false, like does false mean that it's an error? Does it mean that it succeeded? It's not a really efficient way of doing things, but it's like basically the best that we had with Objective-C. Error scribbling and code crashes. So there was situations where if you tried to look at the error, it would crash your application. It would completely scribble over what the error was. So there's absolutely no way of going in and figuring out what the error is. If you want to hear a nice long rant about it, there's an edge cases where Wolf Wrench talks about if you look at the error, you will crash. There's also like it was verbose and it was easy to forget how to handle all the error states. So like I've got an example of part of an error handling thing. So we have this giant long block of code. You have all these things like self, error for whatever, mismatch positions, you have all of these things. And this isn't even all of the code that you would need to actually implement an NS error. This is just part of it. So there's even more code that I don't have up here showing about how to implement error handling Objective-C. This was a pain in the ass. Nobody likes doing things like error handling because, it's like unit testing and other stuff that we don't like doing. So because it's not fun, you don't get to go in and write code. So a lot of people just said, no, this is a pain in the ass. I'm not doing this. So I mentioned we were doing a different kind of error handling than we have available in Swift 2. Back when the language was first released, Brad and Rob Napier and a bunch of other people were debating about how to go about doing error handling in Swift, and they came up with this result type thing. So you create an enum and use generics in order to be able to bring in in order to be able to return more than one kind of value. You can return either a success or a failure. This forces you to handle the errors if you want the success value. There's no need for magic constants because basically you're able to go in and customize all of the errors. And it allows us to use the error type other than NS error, like custom Swift enum. So we have a lot of different kinds of error types that we created over the last year for our code. We have specific robotics errors, we have specific communications errors, we have specific electronics errors. So we're able to get a much better, more accurate viewpoint of what exactly in our code failed. So this is what we were using for the first, year or so that Swift was out, was we were using this enum of result type. So we had two cases, we had a success and a failure. And then we also created this .then function that takes in a function as a parameter that can return either a success or failure. We run our function, and then we do a switch statement on it. So if our function failed, we have an error, it returns what the error is. If it succeeds, then it goes and it calls the next function that we passed into our .then. This is an example of a monadic bind. So you all can go home and say that you were able to talk about monads while you went to this conference. And again, I mentioned that we had enums of different error types that we had for things. So in this case, we have our robotics errors. We have our mismatch. There are a couple of different errors. We have mismatched position, hidden obstruction, or not connected. So we can go and we can implement a move to coordinate function where we're going and we're moving over, down, recurrent coordinate, and we're able to chain a large series of functions that all take this target coordinate as a thing. So when we do that, then we're passing in what our next function is. That then next function. If any one of these fails, it kicks out, it bubbles the error back up to us, and we're able to go in and see where in this chain of actions our code failed and what the exact error was. Now this was really cool. This was a huge advantage over NS error, but it still was kind of clunky. So, I don't know if you noticed, but oh wait, I'm talking about the advantages and not sorry, that's the next slide. So this is a lot better than the NS error because we had compiler enforced error handling for the return value. So we made sure that we would always get, if we were expecting a robotics error, we always got back a robotics error, that we didn't get a communication error and we didn't get an electronics error. This is something that still has not been implemented in the error handling in Swift 2.0, so fingers crossed for Swift 3.0 that we have compiler-enforced error handling. Uses a lot less code. You saw that giant block of NS error code that we had that wasn't even all of the NS error code. This was like 38 lines of code. This was 12 lines of code instead of 38. The inputs are inputs and the outputs are outputs. We're not going in and passing in a pointer that we're then going and like mutating and changing into something else. We're able to pass in our value and get back out an error. And then this is more human readable. So like we can go through and you can read through it. You see, we do this, then this, then this. And so you can kind of read through the code and kind of go like, okay, I think I kind of understand what's going on here, instead of it being like this weird, like blobby alien NS error code. So this was an advantage over NS error, but there were a couple of issues. We had this weird code flow. Like I don't know if you noticed, but instead of having the return statement at the bottom, we had it at the top. So we had return, and then we were going through and we were chaining all of these functions together, and then at whatever point things kicked out, either with a success or an error, we then return back to the top and return whatever we had. That looks kind of weird, especially like for us programmers, where we expect the return to be kind of at the bottom. Sometimes when we'd have really long chains of these .then statements, it would choke the compiler. Like we literally have functions in our code that have 20 chained operations that all need to succeed in order for this to return successfully. And we got to a point where the compiler just was like, after about 12 of them, says, I can't deal with this anymore. Because it confused the compiler because it was really complicated. And then we have like these weird awkward closures where if you didn't have a return result, because we had some things that were void functions, we were kind of setting it up with the idea that we're always going to have to pass in the target coordinates parameter. But we have different functions that are void, so we had to do kind of a workaround in order to deal with the edge cases where we didn't have something that was being returned or being passed in. And then like it was easy to ignore errors for functions that don't return values. So just there were things, this was an improvement over what we had before, but again, this is something that could have been better. So then again, this guy like went and tweeted about a nice post that Brad wrote about this error handling and how it was different from what we were doing before. And I'm going to have a link to this blog post along with a couple of others. But like basically, we went through and like seriously at WWDC when they announced the error handling, I was like sitting there with my computer and my boss was like, quick, go, like download the book. I want to see what it does with error handling. So he's like sitting there like, come on, like download. So I went and he spent the entire like WWDC like looking through the new Swift book to try to figure out all of the Swift 2 error handling stuff to find out about how it was different from what we were doing and to see if it was something that we wanted to implement. So Swift 2 introduced this try-catch error handling model. And if you look at it at first and you're coming from Java, you're like, oh god, this is that kind of thing. Ugh. But even though it looks different from what we were doing before, it's actually very much the same under the covers. It's not like the NS exception, it's not like Java error handling, it's its own thing, and it's really nice and easy to use. And the compiler forces you to handle or rethrow every error, so basically if you don't handle your errors, then it's not going to let you run your code. So this is different from what we had before, where it was totally possible to just ignore all of your errors. So now you actually have to physically make sure that you do something that is stupid and unsafe in order to be able to get your code to compile if you don't want to handle your errors. So we've got our nice little like do, try, catch, throw, and throws keywords. So if you have a method that can provide an error, you specify that it throws in the method signature. If you call an error throwing function, you must call it with a try. So you must try the error throwing function. And the first try line that fails kicks you back out of the function. So in our nice little thing where we had our chain of 20 functions that all needed work, if any one of them fails, it kicks back out. To catch the error, you need to do the do catch. And to bubble the error up, you have to throw the error. So now we're back to our move to coordinate function. So instead of having this awkward return statement up at the top, we're trying each one of these functions. As you can see, the first one doesn't have a parameter in it, so we are able to still deal with the error, and we don't have to do this weird finagly like working around thing that we were doing before, where we weren't able to call a function that didn't take a parameter. It will go through, simplifies things a lot better. Again, we still have the same type safety, we have fewer lines of code, and it's a lot easier to read. So we have 9 lines of code instead of 12. Again, natural execution flow, fewer braces, we didn't have these weird artificial closures, and we have the compiler for error handling. So it's easier for us to deal with the ones that didn't have any values. But again, we don't have it where we can make sure that we're getting a robotics error when we expect a robotics error or an electronics error when we expect an electronics error. Again, hoping that'll be a Swift 3.0 thing. But this was a real win. This was really awesome that we were able to go in and implement better error handling in our code because it's really important when you're dealing with hardware. I mean, it's also important with software, but it's not going to generally cause the same kind of damage. So right now, like I said, we just became feature complete about 3 weeks ago. Our code base is 75% smaller than the legacy code base we had before. I did want to put in a caveat that our code base was kind of unique in that a lot of our code was based on our own internal application logic. So most of the code that we had dealt with our own internal structs and classes. Like we had a lot of robotics code and we had a lot of electronics code. And so not a lot of our code interacted with Cocoa frameworks. If you're going through and you're doing an iOS application that is primarily a bunch of views, you're not going to see the same return on investment that we did because the way the frameworks are set up, they're set up in a way that you have to set a lot of different things. You can't go in and change the way that stuff is because you're interacting with a framework and classes that have existed for a long time. But you'll still see an improvement, especially if you're going in and you're rolling your own classes and structs. Removed whole classes of bugs so that they can't happen anymore. And we identified a lot of subtle bugs that would have taken weeks to track down and cost thousands of dollars of damage. And we were able to actually go in and learn from the mistakes that we made over the last 7 years when we were originally building up the application. So we could go in and architect it in a way that made it easier and more stable to build out and add features. So that was a really awesome thing. We now have unit tests that could not be implemented because of the code coupling. Again, with Xcode 7, we're able to go in and do the code coverage to make sure that every single part of our code was being tested. And we're able to do more sophisticated unit testing. One of the things that we did was we had a fake robot and a fake serial port class that we were able to use for testing so we wouldn't have to connect to hardware in order to go in and do stuff. So in our fake serial port, we could go and we could set it up where it would return specific errors, or we would mimic what would happen if we were actually interacting with real hardware. And this was something that just wasn't possible before when we were working with Objective-C. So our code is a lot safer. It's a lot easier to build up and add new features. It's a lot smaller. And again, we were able to go in and take all of the things that we did wrong the first time, we were able to fix them. And this took 10 months for us to do. It was just my boss and I. So it was 2 people working on a legacy code base that had, I'm trying to think, I should have put in the slide how many lines of code we had, but we reduced it by 75%. We were 2 people, 10 months, and we got this done. And that was while he was working on other things too. So we were able to actually go in and do a lot with just 2 people in Swift to make the code a lot safer. So there were a couple things in the slides that I kind of mentioned. So we've got a couple of blog posts by Brad, why we are rewriting our robotic software in Swift, and his Swift 2 error handling practices. I have an 11-page blog post about our property lists and user defaults in Swift serialization. So if my explanation wasn't necessarily the best, you can go back and you can spend all of your time on the plane reading my long-ass blog post. This is a link to the Llama kit, which is what we were using initially for our error handling before that was introduced in Swift 2.0. So if you're interested in seeing what we were doing to kind of work around it before, there's a link to that. And then we also have the, if you look at the error, you will crash link. Do we have questions?
This is kind of going ways back.
You should have just yelled at it.
The available init that you had for the property list, available init is huge. So I saw at the top you just had if you don't have a thing, return nil.
Yeah.
You have to declare all your properties as force and wrap options or something to make that work.
It was checking just to make sure that what was being brought into the, we were going to try to initialize the, that's a good question.
Because every time I try to do that, it gets real angry if you return nil before you at least put some sort of value in it. The only way I've been able to get around that is by having everything be a force and wrap option, which I hate.
That's it.
So I saw that you had those 3 coordinate properties where if those were non-optional,
Yeah, that could be. I know that initializers with like structs and classes are like different. They behave differently, so it might be that. I will find out. So again, do structs. Structs are better.
This has nothing to do with your code. Why do people want very precise amounts of food in very precise position?
Okay, I probably should explain that better, and I apologize for that. Our robotic system is primarily for scientific research. So it was originally developed with the idea that it was going to be used for biological research. It was created to produce protein microarrays. And I know that one university used our system to actually print like a functioning living cell. We'd like to eventually try to see if we can print stem cells, but we haven't had any universities approach us about that yet. But primarily what we're using the robotics for is printed electronics. So we have a lot of conductive inks that come from places like Xerox that we go in and we're able to print circuits on different types of surfaces. Like I know one of the clients that we had was the U.S. government defense department that wanted to be able to print like ID, like RFID things on flexible surfaces. So you can print like a homing beacon on something that can be put into like a helmet. So if you were a soldier that was out in the field and went missing, they'd be able to track you down and find out where you are. So this wasn't for like, this isn't a consumer thing. This is for research.
Did you just give away like a national?
No. Our NDA on that has lapsed, and it has been publicly presented somewhere. So I no.
Because that camera up there keeps looking at you.
Yeah.
Give me the side eye.
Was that a movie?
It's because it's struck. Available in its instruction on page.
So see, everybody should use Structs. That's another reason you should use Structs is the classes. Thank you for looking that up.
There are APIs in Swift to get the properties of the struct so that you could automate that serialization a little bit so you don't have to write by hand dictionary values where you could say for a given type, what are the names of the properties, and then
I don't think that those have been built in yet. I think, like I said, we went in and we basically rolled our own thing by just using the language to go and build our own serialization. So I don't think that there's anything built into that. But I think that based on what I showed you, and I can show you another like my libxml wrapper, so you can kind of get an idea about how you can write your own thing that'll be genericized and you can apply to a lot of different types of things and be reusable. You can open source. I mean, for me, I took over the Swift tutorial team for Ray Wender like about a little over a month ago. And one of the reasons that I'm really excited about Swift is because of things like that propertyless serialization. We don't have a framework in Cocoa or Objective-C. We don't have a framework in Cocoa to do stuff, but we are able to actually go in and take the language and be able to do things more efficiently than we were before. And I think there are a lot of like real wins for doing things like the JSON serialization and this NS data serialization that I'm really looking forward to doing. I want to find other things that were done kind of inefficiently with the Cocoa frameworks because they were constrained by Objective-C and be able to like explain to people how you can take Swift to make them better. And that just really excites me about what's going to happen with this language over the next 5 years, and being able to find all of these things that we just kind of were always doing the same way constantly just because that was the way to do it, and we start rethinking about how we actually implement things. Yeah?
practical application of your magic constants that when you're interfacing with anything third-party camera device, network, you have to know what 64 means.
Yeah.
But when you create an enum, it's just a sequence of the raw values are just a sequence of numbers and terms. So where are you putting your raw, or where are you putting your constants in your new paradigm of structs? Something has to live somewhere.
Okay, so what we're doing is we'll have a list of different error types. Like let's say that the camera is not connected to robotics.
Right.
In our code, at any point we have a place where we would go and connect to the camera. If that fails, we return the could not connect to camera error. So that's kind of that is our magic constant that we have.
Is that as a struct inside struct?
That lives inside of an enum. So we have an enum of error values where like I said, associated like.
You're explicitly setting each enum's value to the magic constant.
But the magic constant isn't like an amorphous number that doesn't mean anything. It's string description telling us exactly what the problem is.
I understand that. So where I'm disconnected is in the real world, this robot is giving you a 64. But your code has an enum that doesn't know anything about numbers
Well, we do that. We do that internally. So like when I was doing my testing for the 64, like we would go in and we would do that internally in our code. But when we were going and running the code, instead of getting back to 64, we're getting back that we had a camera disconnection.
So you changed things on both sides. You were able to change with maybe I'm not understanding.
Okay, so we're receiving a message from our hardware telling us that there's an error, or we're receiving a response from our hardware. We know what our error responses are, and we're going in and we're wrapping those in Swift so that when we go and run the code on the computer, instead of getting like an error that says you have error 60, you have a segmentation fault 11, we're wrapping it within our code so that when we run it and we see that we're getting an error, it doesn't say segmentation fault 11, it says the camera's not connected. So we're making it human readable so that we're able to go in and debug it faster instead of having to be like, okay, I just got an error that means absolutely nothing to me.
Where does that wrapping occur? Where is that level of wrapping? You know, the 64 gets translated. I think it's basic, but I'm just trying to understand. I like to get all those.
Okay, so in this particular function, like if it gets all the way down here, it's happening right here. We're returning this failure state of this map position. And all of these other functions that we have up here have a similar thing where it will either return a result or return an error. And we tell it what the error is. So this is where this is getting wrapped.
Okay. And this is running on the map that's controlling the
Yes.
robot.
Yes. You really are.
I guess I'm still confused with where the 64 is. Maybe
Okay, that was the thing that I was working on that I don't have like here for my code. But basically, like, so I'm going in and I'm running a function where I'm checking what. So I'm sending bytes out to the serial port, and then I'm getting bytes back, and I'm reading those bytes, and then I'm processing the bytes. So I'm saying like if the bytes say 64, then I know that there's an error, and I'm returning an error. And if it's not an error, then I'm calling the next function and passing it on to where it needs to go next. So I'm returning what the bytes were up at the top of the function so that I can use that to be called in another function that needs those bytes in order to process it, in order to process things on the serial port. We can talk later. I was going to say, like, most of our code we were able to do in Swift, but we had one thing that we weren't able to do. We had an old C library that we used to connect to our camera. So our camera is a FireWire compliant camera. Since the company's been around for a really long time, back when we first started, all of our cameras were FireWire. And then when FireWire went away, there were a couple of USB 3 cameras that were FireWire compliant. So we had an IIDC camera library that we were using to connect to our cameras that utilized C immutable function pointers. And right now, Swift does not allow you to work with C immutable function pointers. So we have one set of Objective-C code in our code base because we were utilizing this old C library. But generally speaking, like everything else that we were trying to do, we were able to do in Swift. It was just that one thing where we were talking to an old C library. So like a lot of people were talking about like, oh, Swift isn't ready for production. There's no point in writing like code in it because we do everything. We got to do everything we needed it to do. And then the one thing that we didn't need it to do, we just added a Objective-C bridging header, and it wasn't a big deal. More questions? Around until 3 o'clock. All right. Well, thank you very much.